In this part of section 6.3, we're tasked with finding the value of a normal random variable. That means we want to go backwards. If we're given a probability, find the value, versus what we did in the first part, which was here's a value of x or of z. What's the area under the curve to the left or to the right? Now we have the area or the probability, and we would like to find the value of the random variable that's associated with that area or that probability. So to do this, we need to use the z-table in reverse. And by reverse, I mean we have to look up the area, find the area in the body of the table, and then read the associated z-value. So this can be kind of tricky because you're looking at a lot of numbers inside the table, but at least they're not random numbers in there. And we'll practice just using z-values, and then we'll look at some applications. To find the z-score so that the area under the curve to the left of some z-value is 0.2. Think about what that means. Here's the distribution. It's normal. The mean is 0. And there's some values, some z-score somewhere here, probably negative because 0.2 is less than half, so that the area to the left of that z-value is 0.2. What value does that? Which value has a table value or a table area close to 0.2? How close to 0.2 can we get? To do that, we need to look at the actual z-table. Pulled it up here. We want an area of 0.2. You'll notice that these tables, or these z-values, are already positive, which is not going to give me the area I need. They're all bigger than 0.5. So we'll go to the other side, or back up. Here are some values that are 0.2, 0.21, 0.209, 0.206. I'm getting closer. This is 0.2005, and the next closest value is 0.1977. So I need the one that is closer. That's 0.2005. So that's the area to the left that I'm looking for, the closest I can get. Now I need to read the z-value from this area. That's in this row. And this column. So I know that the first two digits of the z's value are negative 0.8, but to read the next digit, the hundredths place, I'll have to go up on the table all the way up to find the next value. The last digit is 0.04, so I have negative 0.84. We'll have an area to the left of 0.2. Now if we rephrase the question and find the z-value so that the area to the right is 0.35, the mean is still 0. The area to the right of 0.35, so there's some z-value so that the area to the right is 0.35. Now we have some choices. The table doesn't give us right away area to the right. We could look for the z-value on the table that has 0.35 to the left. And because of symmetry, that will be the negative of the z-value we're looking for. Or we can take 0.35 away from 1 and see what all the area to the left of that z will be. 1 minus 0.35 is 0.65. So we could look for 0.65 in the body of the table or 0.35. If we do 0.35, we'll have to flip the sign of z. Those two values should be the same. So let's take this first approach by symmetry. Look for 0.35 in the table. .35 inside here. Here's 0.33, 0.33, 0.35. 0.3520 looks to be as close as I can get to this score. Let me make sure. 0.3483 might be closer. 3594 definitely not. So really we're between these two. Which one's closer? And to answer that question, if you don't have a good feel for this, we'll look at the difference between the number we want, 0.35, and the number we can read from the table, 0.3520, and see which one has a closer value, or 0.35 minus 0.3483. Which one has a smaller difference? And that answers this guy, not what I would have chosen on my own number sense. Good thing I checked. So 0.3483 is closer because the difference is only 0.001 versus 0.002. Now I need to read that value so I know that the first two digits are negative 0.3, and the last digit, if we scroll up on this column, we see it's 9. So the z value is 0.39. We read negative from the table, but we want the positive version because we're looking for area to the right. Alternatively, we could look for 0.65 inside the table. Let's confirm our findings with 0.65. So inside the table I need 0.6, there's 64, 6480, 6517. I can tell that that's closer to 0.65. 80 is 20 away, 17 is only 3 away, so from 652, so 6.6517, we're 17 away or we're 20 away. So this guy's the winner, he's closer, that's 0.39. So that confirms what we found using the symmetry. So if we looked for this area to the left, we also found that z was 0.39. So that's how we can find values from the z-score, to the left or to the right. You can try C and D. The answers are in the lecture notes, so you can see if you did it correctly. You might pause the video now and try that. Another way you can ask the question, and this leads up into some things that we'll be doing in later chapters on inference, is we'll find the z values that separate a middle of the distribution. We want the middle 98%. So the mean is at 0. There must be some value of z. It's symmetric, so we'll take the plus and the minus version of that value that will separate. So we have 98% of the area under the curve between those two values. So if 98% is between, we can think about what's left over. The leftover parts, the parts in the tail, would be 1 minus 0.98 or 0.02. And then the curve is symmetric again, right? So there's 0.002 divided by 2, which is 0.01 in this tail. And there must be the same amount of area in this tail. So from there we can read inside the table what z-score has an area to the left of 0.01. That will give us this left-handed z-score. Let's check it out. 0.01 must be pretty small. Here's 0.0107. I can probably get a little closer with 0.0099. That guy's only 1/10,000th from 0.01, so that's negative 2.33. By symmetry, the other cutoff would be positive 2.33. So I know that these z-scores, plus or minus 2.33, cut off the middle 98% of the standard normal distribution. The next one you can compare, try it yourself, and you can see what the answer in the lecture notes say. If we want to extend this idea to some applications, to some actual probabilities where we have like x values and a different mean and different standard deviation, not just 0 and 1 like we do in the standard normal, we have to do the two steps we did in the beginning of this section in reverse. And that means first find the z-score from the table. So here we look at the table first to find the z-value that's associated with the area or the probability we want, and then we can calculate the x value, the specific value, from the score we have for z. So x is z times sigma plus the mean. This comes from the fact that z is x minus the mean divided by the standard deviation. We simply did some algebra to solve for x. We don't make you do that here. You can take an algebra class if you like, but that's where that formula comes from. You can use it, don't worry about it, it'll be on the formula sheet, so don't spend too much time reinventing the wheel to solve the standard score for that. So to do some of these. The reading speed of 6th grade students is approximately normal, so that lets us know right away we can use the normal distribution. The mean speed is 125 words per minute and a standard deviation 24 words per minute. We're looking for the reading speed of a 6th grader who's at the 90th percentile. And remember from numerical descriptions of data, measures of position, the 90th percentile means that this student reads as quickly or faster than 90% of the other students. That means the area to the left of this student's score is 0.90. So to answer this question, we need to find the z value for which 90% of the area is to the left. So find z for which the area to the left is 0.90. We'll go back to the table and look inside here. We want 0.9, so that will be somewhere in the positive z's table. 0.90, 0.8997. That's very close. 3 10,000ths from 0.9. So that value is 1.28. So that's how many standard deviations we need to be from the mean. So now we want to calculate what value of x, what reading speed is that. So x is z times sigma plus the mean. For this application, z is 1.28. The standard deviation is 24, and we're going to add the mean of 125 for a reading speed of 155.7 words per minute. But who reads 0.7 words of a minute? So we'll just call this 156 words per minute. Now the psychologist wants to determine reading rates for unusual students, and you may have experienced this in school where you go out to the classroom and you read with a reading teacher, a teacher's aide, and they just kind of count how many words you can read in a minute, how many mistakes you make, give you an accuracy, and then if we have somebody who's unusual, either high or low, we might give them a little extra attention, either to catch them up or to keep them from getting bored. So of course we would be interested in these unusual students who read quickly or more slowly than the middle 95%, we're going to say. So think about the picture. Here's a curve, normal curve. There's some middle 95%. The mean for this curve is 125. That's reading words per minute. A specific application, but there must be some cutoff, some x1 and x2 value that separate the middle 95%. To find the z values associated with the score, we're going to use the area to go to the table to find the z. So we need to realize that 5% of the area will be outside on the tails, and that will be divided in two because of symmetry. So right here we have 2.5% or 0.025 in this left tail, and the same area here, 0.025 up here. So to find the z-score, we want to have 0.025 to the left of this z value. So notice that when we have our curve, we're always looking to find an area to the left that we can look up in the table. 0.025, 0.1, 0.22, 0.28. Oh, looky there, right on the nose. That doesn't happen very often. This one in particular is the one example where it does negative 1.96. So now we know that z is negative 1.96 or positive 1.96 by symmetry to separate that middle half, or that middle 95%. So now we need to convert those z values to x values. x1 will be z1, negative 1.96, times the standard deviation of 24 plus the mean of 125. That value is 77.96. And x2, the second cutoff value, will be the positive version, 1.96 times 24 plus 125 is 172.04 words per minute. So we're going to separate 78 words per minute to 172 words per minute. That's the bracket of the usual, the typical results. 95% of students can read between 78 and 172 words per minute. So if someone comes in less or higher than that, then they would be in the bottom and top 5%, or the top 2.5% and the bottom 2.5%. In industry, outside of education, we use this idea, or manufacturers use this idea so they don't spend too much money replacing their parts. I'm sure you've all had a cell phone with a warranty that lasts like a year, and then at 13 months the thing will break, and that's because they're not dummies when they assign how long the warranty will work. They don't want to be replacing cell phones left and right, so they like to make the warranty right before the expected lifetime of the item is over. In this example, it's about watches. Watches have an average life of 28 months before their electronic components deteriorate, so now it won't work anymore. The standard deviation is 5 months, and the distribution is normal. That's important, not so much in this chapter, but as we move forward, and we have to distinguish what concepts to apply to problems. So if Acrotime will guarantee a full refund on any defective watch for 2 years, notice that 2 years is 24 months, what percentage of the production are they going to replace, or how much should they expect to replace? Here we're not looking for the cutoff value, we're looking for a percentage or an area or a probability. So we would like to find the value from the table. That's 2 steps. 1, find z. 2, look it up in the table. So z is x, which is 24, minus the mean of 28, divided by the standard deviation of 5. The z-score for this problem is negative 0.8. The table will tell us the area we would like to find. So here's the curve, there's a mean of 0. Our z-score is back here, negative 0.8. And let's see, what percentage should they expect to replace? That would be all the area to the left, right? These are watches that they replace until they hit that 2-year mark for guarantee, and then they don't have to replace them anymore after that. So we're simply looking for area to the left of negative 0.08. That's a direct table read. The table value at negative 0.8 is 0.2119. So what percentage are they replacing? Approximately 21% of watches get replaced. So they don't want to do that. They say they don't want to refund any more than 12% of the watches. So how long should they make their warranty? How should they adjust it so that they meet this mark? It's still normally distributed, but now we have some cutoff value for which we want only 12%, 0.12 of the area to be to the left of some x value. And we want to find that x value. So first we'll find the z value for which 0.12 is to the left. Zero 0.12, 11, 10, 12. This would be right between this. So here's an interesting situation. This row has 2 values that are exactly the same distance from 0.12. They're both 1,000th away. So what we could do with this is estimate exactly right in the middle. That's because neither of them is closer, so we're going to estimate which one's exactly in the middle to go up and read the value right between those two last digits. So right now the leading digits are negative 1.1, and if we go up on the table, we see that we're halfway between 0.07 and 0.08, so that would be 1.175. That would be the best approximation. If you're not comfortable with halfway marks between those numbers, then you would just pick 0.07 or 0.08. Either one would be off by the same amount. I'm happy with negative 1.175 for the best value of z that we can find from the table. And then we need to calculate the x value, right? So step 1, step 2, what is the x value associated with this z-score? That's z sigma plus the mean. Z is negative 1.175 times the standard deviation of 5 months plus the mean of 28 months. Says that this watch will, or the warranty should be placed at 22 months if they don't want to replace too many watches. So they need to reduce their warranty by 2 months, and that will save them 9% of replacements. Or they could always make a better watch, right? Okay, so we did all these problems by hand, and now I'd like to go back and show you how to do them on the calculator. The calculator does have the built-in normal distribution function, and it also has the inverse normal distribution. So when we're asked to find the value, we need to use the inverse normal to spit back the value. We give it the area. So to access that, we'll hit the second number in the variables key. That will access the distribution menu, just like we did for binomial and normal CDF and PDF. Pull mine up over here. So second, distribution, normal PDF, never use CDF for finding probabilities, inverse norm, number 3, for finding values of random variables. The area input needs to be area to the left of the cutoff. So even if you're given area to the right, you need to transform it to be an area to the left. That's all the calculator will take as input. So in this first case, we had 0.2 to the left. The mean of a standard normal variable is 0, and the standard deviation is 1. So it's already set up to be standard normal. This guy will give you exactly the value, not the rounded value from the table, but the exact value. See how many digits there are. So a little slightly more exact answer, negative 0.841621, a little bit better than this. Now, if I would like to know the inverse norm, or the cutoff value where I have 0.35 to the right, the area would be 1 minus 0.35, or 0.65 like we did earlier. Mean 0, standard deviation 1 still for standard normal. And then this area by the calculator is 0.3853 to 4 decimal places. But you see, of course, if we were to round to 2, we would get the same value from the table. If you want the area between, you still have the same problem. The calculator needs to know only area to the left, so we still need to manipulate it so we see which area or how much area is to the left of a distribution where we want to separate the middle percentage. You can make the calculation right there in the area. We could say, well, 98% is in the middle, so 1 minus 0.98 will give me the leftover parts, the parts on the outside, and then I'll want to divide that by 2. So you don't have to come up with the actual 0.01 number. The calculator can make the calculation in there, but you do need to realize that it's area to the left and to the left only. So negative 2.326 would round to negative 2.33 as we saw earlier. This is very helpful when we have a distribution that's not normal. So if we look at these reading speed situations where we have a different mean and standard deviation, we can put it right into the inverse normal. It skips the step of having to find the z value. We completely skip the standard normal distribution. So let's do this one where we want 90% of the students to be less than this one student. What's the cutoff? 0.9 will be to the left. The mean now is 125, and the standard deviation is 24. We have a cutoff value of 155.75, so 156 if we round. Same answer. That's from inverse norm. Area to the left, 0.9, mean 125, standard deviation 24, spits out exactly the answer we got by hand. Just simply a little bit faster. You still have to find the area to the left though, so that's your, in the distribution menu, and can shorten it up for you. Your calculator friendly, it always makes it a little bit faster.